Howdy, Padres. We are looking at our next section. This is part 2B on cosmology. We just finished particle physics, and now we're moving on to cosmology. So let's jump to it. Cosmology is the origin and fate of the universe. It's kind of like how everything came to be and what's going to happen. So we're going to start with the Big Bang. The Big Bang is a theory that explains the birth of the universe. You guys are sure have heard of it. It occurred roughly 13.7 billion years ago. Long time. It started from an infinitely dense, infinitely hot gravitational point that was infinitesimally small. That's a lot of infinities. So it's just the math we have that shows what it looked like. It's just infinitely heavy, hot, and tiny. It's crazy. The Big Bang also explains the expansion and stretching of space. It's actually space-time and everything in it. There's a few things that the Big Bang Theory does not explain. It does not explain what initiated the creation. So we have this very tiny, very hot, very dense. Where did that come from? The Big Bang Theory does not explain that. The Big Bang Theory does not explain what happened before the Big Bang. So before it goes, we don't know what happened. We don't know what triggered it. So why did the Big Bang cause? Why did the Big Bang cause? What caused the Big Bang to actually bang? We don't know. And the Big Bang Theory does not explain whether or not God exists or does not exist. And in fact, many famous scientists and astronomers who studied cosmology do believe in God. So it's not like a one or other. Like you can still believe in God and believe in cosmology. They're not exclusive to one another. So the very first part of the Big Bang is called the Planck epoch. And it goes from 0 seconds. So we're talking really hot, dense point to 10 to the negative 43 seconds. That's a very small amount of time. That is a 0.00043 zeros seconds. So from 0 to that, we're talking just like it's shorter than a snap. It's like such a tiny amount of time. It's when time begins. Matter did not exist. So the only thing that's there is just pure energy. Instead of having 4 forces of nature, like we talked about last lesson, there's only one force. All 4 of them are unified. It's one thing, one force. We said this last slide, very dense, very hot, and it's a point. And it expands from that point to 10 to the negative 35 meters. Once again, that is 0 point and then 35 zeros of a meter. Very small. So we're talking in a very short amount of time, it expanded a very little amount. And it is extremely hot. That is 32 zeros after that. So from 10 to the negative 43 seconds to 10 to the negative 36 seconds is called the grand unification epoch. And 2 forces now exist. So you kind of have, it's kind of like when you look at in biology family trees of different species, and you have like the branches, like you have mammals and reptiles, and you have like the different branches. Same thing's kind of happening here. We had one force, and now the forces are kind of splitting. And on one branch, you have gravity, and on the other branch, you have the grand unified theory, which contains the electromagnetic, the strong, and the weak force. And we can actually see the connection in physics and in math between those 3 forces. The leptons the quarks and the antiparticles were created during the grand unification. So we went from pure energy. Now we have electrons, we have neutrinos, we have muons, we have tau particles. Those are the leptons. We have quarks, up, down, top, bottom, strange, charm, and we have all the antiparticles. So all those particles have their antiparticles are created. Nope, I just said that, and I just said that, and I said that. So we kind of went over those last lecture. Okay. The next period, or epoch, is the inflationary. Once again, it's a very small amount of time. Three forces. So we kind of have another branch in the forces. So now we have gravity, we have strong, and we have the electroweak, which is the electromagnetic and the weak force. Universe expands from the size of an atom to the size of a grapefruit. So it starts in this epoch, it starts the size of an atom, and then it goes to, yay big. And this is the universe. This has everything. This has the stuff that makes up all the galaxies, all the stars, all the planets, all that stuff is this big at this point. And they call it a quark soup. It's just thinly and uniformly spread. All of these particles are kind of just spreading out. The electroweak epoch. The four forces of nature are now fully separated from one another. A large number of exotic particles are formed, including the WZ and Higgs boson. W and Z particles, we said last time, are responsible for the weak force and nuclear decay. And we said also that the Higgs boson is what gives particles their mass. So these are created during this time frame. The quark epoch. The universe cools down a lot, but it's still 10 quadrillion degrees Celsius. Still very hot. Quarks, electrons, and neutrinos form in large numbers, so they're still being created from this massive amount of energy that the universe has. It's creating these quarks and electrons and neutrinos. Baryogenesis occurs. Baryogenesis is the annihilation of particles and antiparticles. So because we have all these quarks and electrons and neutrinos, and we have the antiparticles are also around, they're colliding with each other. And when they hit, when a particle hits its own antiparticle, so if a proton hits an antiproton, they annihilate pure energy. If an electron hits a positron, it will annihilate into pure energy. If a proton hits a positron, they'll bounce off each other. They don't annihilate. It's only when a particle hits its own antiparticle, the exact opposite, pure energy. So we have particles and antiparticles colliding, forming energy. However, all of the antimatter gets annihilated. It gets eaten up by the matter, but there's more matter. And because there's more matter, that is why our universe is made up of matter. All the planets, all the stars is matter, and that's because there was more matter than antimatter. If there was more antimatter at the beginning, then all the matter would have been destroyed, and we would have had planets and stars and everything made up of antimatter. Okay. The Hadron Epoch. So now we're finally getting up to 1 second after the Big Bang. So all of this has happened in less than a second. Kind of crazy. The temperature cools to 1 trillion degrees. So that's still a huge temperature, but it's still cooling down extremely fast. Quarks are finally combining to form neutrons and protons. And the reason this is called the hadron is because protons and neutrons are called hadrons, which is another name for protons and neutrons. So protons and neutrons are finally forming. So the quarks are kind of combined. Lepton. So from 1 second to 3 minutes after the Big Bang, electrons and positrons continue to be created. So they're it's not like they just all annihilated and that's it. That did happen, but they're still creating and they're dominating the universe. Remember, electrons are leptons, so this is why it's the lepton epoch. Nucleosynthesis came from about 3 minutes after the Big Bang to 20 minutes after the Big Bang. Temperature falls to 1,000,000,000 degrees. And it's cooling down enough that protons and neutrons are now forming hydrogen, helium, and lithium ions. So we're getting nuclei starting to form, but there's still no electrons bonding to these nuclei. So we have positive atoms. Okay. Photon epoch. From 20 minutes to 240,000 years. We finally got to like a big time frame here. The universe is filled with plasma. It's a hot, opaque soup of nuclei and electrons and photons. And so the photons are interacting with the nuclei. So photons, they can hit an electron, and when they hit an electron, they bump that electron up to a higher energy level. We are going to talk about that next week in a little more detail. But basically, the photons are only interacting with the electrons. They're hitting electrons. They're giving the electrons more energy. And the reason this is happening is because all of this soupy, there's so many nuclei that these electrons are, the photons are just interacting just with those. They don't have a way to escape yet. Recombination decoupling. Temperature falls to 3,000 degrees. And electrons are able to bind to the atoms. So electrons are now, the electrostatic electromagnetic force is causing the electrons to bind and get attracted to those positive nuclei. And when that happens and the electrons are combined, the photons are now free to travel. So the electrons are not floating around anymore. They're actually like stuck to the atoms and it allows the light to travel. We can see this. This is the first observable part that we have actually seen. It's called the cosmic microwave background radiation. It's actually not light. It's actually, we can see it with microwave instrumentation. And it's kind of like, it's the first part of the Big Bang that we can actually see. It's the actual light from the explosion. But it happened at this time because before the light wasn't able to escape, and now the light's finally able to escape because the electrons are now bound to the atoms. And at this point in time, the universe is mostly hydrogen. There is some helium, and there's very little amounts of lithium. This is kind of what the cosmic microwave background looks like. If you look at it through a microwave telescope, any direction you look, you kind of see this, and it's kind of just the remnants of the Big Bang explosion, called the cosmic microwave background radiation. Here's a video talking about the picture of the Big Bang. So minute physics again, take a look. The dark era, from 300,000 to 150 million years after the Big Bang. There are photons, but there are no stars. So it's just a period of kind of darkness. Star and galaxy formation. So after that, between 300 million years and today, gravity is bringing together gases of hydrogen and helium. It combines, it crunches the hydrogen atoms dense enough until it forms fusion, and then that produces stars, and then we get galaxies. Early stars were short-lived. they exploded, releasing heavier elements, which fused into the heart of heavier elements fused in the heart of stars. So we have, during the explosion of stars, they release heavier elements on the periodic table, and then those heavier elements are in other planets and other stars. And so we'll talk about that also in detail next week. So our solar system, our star, and our planets, including the Earth, formed between 8.5 and 9 billion years after the Big Bang. Okay? So many years after the Big Bang is when our solar system formed. And today, the universe continues to expand. So it blew, Big Bang, it expanded. Things are still going out and out and out. Continues to cool and expand. Stars continue to form and die. Our solar system is about 4.5 billion years old. So it started around 8.8 billion years after the birth of the universe, after the Big Bang. 13.7 billion years later, so it's about 4 billion years old. Here's a quick summary. I try to make things even shorter so you can read that. Here's another video kind of talking about it in a little more detail. Take a look. A common question that students ask is, what is the universe expanding into? So if the universe is everything, the universe is all stars, all light, all planets, all everything, and it's expanding, what's outside the expansion? Very common question. Watch the video if you're interested in finding out the answer. All right, dark matter, dark energy are the last two topics. We know they exist because we can see the effects of dark matter and dark energy. And the effects show us that there is a lot of it. However, we can't see it. So when we look for it, it's basically invisible. To kind of show you an idea of how much of it there is, everything we see is only 5% of what's actually there. 27% is dark matter, and 68% is dark energy. So what we know about physics and what we know about stars and planets is only 5% of what's really there. And the rest of it, we know it's there. We have evidence that we know it's there, but we don't know what it is, and we don't know anything about it. So here's a little demo. You guys can try at home. You can watch this. Basically, I have a string on a rope or wire. It's tied to something heavy on the end. And I'm going to swing it in a circle over my head. I'm going to ask you some questions. The rope that's swinging and the weights are simulating a spinning galaxy, a galaxy that's swirling. Your hand that's holding it is acting as gravity. So it's the gravitational force that's holding all those spinning stars together. If there is no gravity and you let go of it, all the stars are going to fly away in different directions. Gravity is holding all of them spinning, just like your hand is holding the weight in a circle. And what I want you to do is swing the rope at different speeds. So swing it slowly and swing it fast. Please go outside. Don't do this inside. And feel how hard it's pulling on your hand slowly, and how hard it's pulling on your hand when it's spinning fast. Compare it. All right. So the solution. So go out and try it. Pause the video if you don't want to know the answer. You can watch this video. Like I said, I kind of do it and explain it a little bit. But the answer is, the faster it spins, the more force is needed to hold it. So the faster you go, the more it's trying to pull to escape. So for galaxies, this means that the faster the stars are spinning, the more gravity is needed to hold them together. So we got this galaxy spinning, and there's gravity that's holding it all together. When we observe galaxies, they're spinning much faster than the gravity that we can see. So we can calculate the gravity that's in this because we know we can look at all the stars and we can kind of predict how much gravity is in this galaxy. And the number we get is much, much less than the gravity needed to hold those there because they're spinning so much faster. It'd be kind of like if you're spinning a rope and it's spinning super fast and it's barely pulling on you. It doesn't make any sense. So what that tells us is there must be some other mass that is unseen, giving the galaxy enough mass and gravity to keep the stars in orbit. So there must be something there. We don't know what it is. We can't see it. We can't detect it. It doesn't interact with light, so it doesn't bend light. It doesn't change light at all. But we know it's there. It has to be there because it's spinning too fast. The stars are spinning too fast for it to something not to be there. Dark energy. So we know gravity should pull galaxies together. So the universe is expanding. Gravity pulls things together. So eventually, if there's all these items on the outside, gravity should kind of pull them back together. So we should see the expansion slowing down. If you have an explosion and it's going out, the gravity should slow it down. And then eventually you would think the gravity would pull it back together. What we observe is the opposite. The expansion is accelerating. So not only did it explode and expand, but it's expanding faster and faster and faster and faster. This makes absolutely no sense. So there is some unknown energy, we call it dark energy, that is causing this acceleration. So we think space is expanding. There's something in space that's causing it to push out further and faster. But once again, we have no idea what it is. So we call it dark. Another video talking about dark matter, dark energy. Take a look at that. And the fate of the universe. We don't know what's going to happen. We don't know what the ending is going to be. The reason we don't know what it is because we don't know what dark matter and dark energy is. So because we don't know what it is, it's hard for us to determine what's going to happen because most of the universe is dark energy and dark matter. So without knowing what it is, it's hard to tell what's going to happen to the universe. However, we do think that there are three options of what could happen. Something called the Big Freeze. The universe keeps expanding. Stars eventually are going to die when they run out of fuel. And when they die, they're going to get cold. Everything's going to get spread out. Everything's going to freeze. And it's going to be cold and dark and kind of depressing. That's the Big Freeze. The opposite is the Big Crunch. If we can find out that gravity has a pull and somehow gravity is going to slow this expansion down, gravity can pull it all together, it can crunch back together, maybe cause another Big Bang. Maybe this happens over and over again. Maybe we have a Big Bang and then a big crunch, and a Big Bang and a big crunch. Maybe it oscillates. Currently, this one is not looking good because, like I said, it appears that things are accelerating and speeding up, not slowing down from gravity. The last one is the Big Rip. The Big Rip is the space between particles expands so much that forces can't hold things together anymore, and it causes molecules to rip apart. So if space is expanding, things are expanding and the space itself is expanding. If it expands so much, then the strong force that is holding protons together, if the expansion is bigger than that, if things keep accelerating and that expansion gets bigger than the strong force, it could just rip apart nuclei. In which case, atoms won't be able to be possible anymore. And so you won't have atoms, you won't have stars or planets or anything sticking together anymore. So which one of these is going to happen? We don't know. Video talking about just what I just said. about the 3 ways the universe could end. And that is it. Next week, we are going to talk about stars. But that is it. So thank you for tuning in. And as always, please ask if you have questions. Please do the problems for cosmology. They will be due Friday, 11:55 p.m. Have a good day, Padres.